Hi, welcome back to the Level 3 Cambridge Technical Engineering. It's Unit 4 Principles of Electrical and Electronic Engineering, and we're looking at two different papers, looking at Tuesday the 17th of January, and we're also going to be looking at Tuesday the 24th of May. So if we slide that paper out of the way, you'll remember in the last video that we looked at Ohm's law, we looked at a resistor acting as a load, we looked at an ammeter measuring current, we used V over I equals R, Ohm's law, we covered the I, we did a calculation of volts divided by resistance to give us current. We also did a parallel resistor problem. We added the two resistors together, parallel correction, series resistor, they're in series, a series resistor where we added the two resistors together to get a total resistance, and then we divided the voltage by the total resistance to give us a more accurate current, and then we calculated power, which was the voltage times the current. We used the most recent current because we were following the logic of the examiner, and that brought us to the power being 3.29, and I asked you to go away and find out what would be the unit for power, and hopefully you've come up with watts, capital W, because Watts is the scientist that proposed the sort of power formula, and therefore we use capital W like to amp, capital A for amperes, capital V for volts. So we sort of honour the scientist, if you will. You'll see this throughout science and engineering. So if we now look at Tuesday the 24th of May, and we look at question 1, we see right away that we've got a question that says calculate the energy used by, and it's talking about a fan. An electrical fan is rated at 300 watts. This one's 3.29 watts for a small resistor. This is 300 watts for a fan, and it's connected to a 240 volt supply for 5 hours. So you can see that these first questions, if you will, reflect the sort of specification in that they deal with some basic Ohm's law to start off with. What we're going to do this time is, last time I walked you through the problem, so what we're going to do this time is we're going to start you off with question 1a. So I've got an electrical fan, so I've got 240 volts. Again, like I said before, I like a little sketch. So there's my fan. That is not the symbol for a fan, by the way. That's just a sketch. There isn't a symbol for an electrical fan. I'm just drawing the question to help me understand it. So we've got 300 watts here. What do I know about that? Just before I think about it, what I know is that watts is V times I. So P is equal to V times I. So this number, this 300 watts, is going to be made up of 240 volts. 240 volts. So the power here is 240 volts times something. So I'm sort of applying knowledge by understanding that power in watts is V times I. Well, I've got V, so actually I can almost predict that the question is going to be something to do with figuring out the current, because I don't have that value yet. So we'll have a look at the question now. It's saying calculate the energy used. Now, energy is slightly different from power. Okay, energy in this circumstances is basically the amount of power is watts per second. So here we have 300 watts per second is effectively what we're saying here. So every second this fan will use 300 watts, and it's going to do that for 5 hours. So that's 300 watts every 1 second. So every time there's a second it's got 300 watts, then 600, 900 and so on and so on. So there's a little bit of a calculation then to calculate the energy which is P times T. Okay. Now energy, as you'll know from science, is in joules. Okay. So if we look at what power we've got 300 watts times, right, let's just take a second, pun intended, 5 hours. Okay, well 1 hour equals 60 minutes, that's 60 seconds. You've got 6 6s are 36, so 1 hour is 3,600 seconds. We've got 5 of those. 6 5s are 30, carry the 3. 3 5s are 15, 16, 17. We've got 18,000 seconds. So we've got 300 watts, 18,000 times. So, switch it on, 300 watts, 18,000 seconds equals 54 0 0 0 0 0 1 2 3 1 2 3. So 5,400,000. Being an engineer, I much prefer 1 2 3 4 5 6. It's going to be 5.4 times 10 to the 6. So if we think about our prefixes, and this is good revision, is to get yourself familiar with your prefixes again. So we've got kilo, which is times 10 to the 3. We've got mega, 10 to the 6, and we've got giga, 10 to the 9. Okay, so 5.4 mega joules. Again, capital J, named after a scientist, joules. And these are going to be really useful to keep track of, because we're going to go in the other direction as well. We'll be talking about things like milli, micro, and nano, which is minus 10 to the 3, minus, or 10 to the minus 6, and 10 to the minus 9. Think millimeters. We talk about microfarads in electricity quite a lot. Okay, 10 to the 6, and then we have nano, 10 to the minus 9. Okay, so do make sure you know these and practice them, because you might sometimes be asked to produce an answer in those values. And it's very important that you understand the times 10 to the 3, 10 to the 6, 10 to the 9. And to be honest, I'll show you some examples later on. It does make a lot easier for you. If you can get practiced in using this, it can make some of your sums very, very easy. So, energy is power times time. We had 300 watts of power, that's 300 watts every second. So we had to figure out how many seconds we've got. Well, that was for 5 hours. So we looked at 1 hour, which is 60 minutes, which has 60 seconds per minute. So 6 times 6 is 36, and the noughts, we have 3,600 seconds. Multiply that by 5 for 5 hours, we've got 18,000 seconds. Multiply that by the 300 watts, gave us 5.4 megajoules of energy. So that's how much energy would be used in that 5-hour period. Take time to have a look at that. And the one I want you to do, because we've illustrated one, the one I'm going to ask you to do is this one. It says calculate the current drawn by the fan motor. Okay, so I'm going to refer you back to this. I'm going to suggest that you have a look at question 1, A, part 2 yourself. So slide that in there. Calculate the current drawn by the fan motor, 2 marks. I'm going to pause the video. So, what was your approach? Oops, just dropped something there, sorry. So what was your approach to this? And hopefully this is where your maths and your knowledge of maths comes into play, because you can start to use some basic algebra. We know the power was 300 watts. We know that the voltage is 240 volts. So we're multiplying it by the current I, which is something that we don't know. Algebra to cancel out the 240 volts. It's multiplying here, so you would divide by 240 on this side. You always do the same on the other side, so we're going to divide by 240. So we'll end up with 300 watts divided by 240 volts is equal to I, which is going to equal 300 divided by 240, 1.25. 1.25 amps. Which again, thinking about it, 240 volts sounds like something you plug into the wall. We use 13 amp plugs. More than 13 amps would be dangerous. You know, there's a safety factor. So it's saying here 1.25 amps. That seems a perfectly reasonable value for the idea of something like an electrical fan on a 240 volt supply. So what we've got then over the first question for both papers, we've got Ohm's law relating to power being the voltage times the current. Okay, so if you've got power or you've got voltage or you've got current, you can move backwards and forwards through these values. The same with Ohm's law, and we introduced the concept of energy used being power times time in seconds. Remember, we're using SI units. Yeah, if it's not in SI units, the first thing you should do is convert it into SI units. You shouldn't get anything in the exam that's not SI units. Energy is equal to power times time, and the value, or the SI unit for energy, is joules. And that's question 1 for both papers. And we'll look next at the second part of both these question 1s, slightly more sophisticated bits of theory involved. And we'll see you in the next video.